Hello, my name is dgarciadiaz, and this is my final project for ECEN 520. My project is titled Diabetes Risk Prediction. This project focuses on a comparative analysis of different modeling approaches for the detection of diabetes. The project addresses a large-scale binary classification problem. Its aim is to predict the probability of a diabetes diagnosis. The training and the testing datasets were pulled from a Kaggle challenge titled Diabetes Prediction Challenge, also known as the Playground Series S5E12. Datasets for this competition were generated from a deep learning models trained on the Diabetes Health Indicator dataset. The training set had 700,000 records, and the test set contained 300,000 records. I found that the training dataset was composed of 62.33% cases of diabetes diagnosis. The primary success metric, as defined by the competition, is the area under the arrow C curve, or the AUC. The data contained 24 features, with only 17 of them being relevant, such as BMI and age. I introduced 3 new features to aid in the detection of the diabetes diagnosis. First, I introduced the LDL over HDL cholesterol ratio. This is a strong predictor of cardiovascular and metabolic risk, which contributes to an increased risk of diabetes. Secondly, I introduced the BMI by age interaction feature. It is well known that those with a high BMI in combination with an older age are at higher risk of diabetes. And finally, I introduced age binning. Diabetes risk does not increase linearly with age. In fact, certain age groups are at higher risk than others, and therefore it is best to create categorical age bins to represent this. I prepared the data by applying a standard scaling to all numerical features and also the one-hot encoding. The end result had high dimensionality, which became a key challenge for the optimization portion of this project. I attempted to train 3 different models on the dataset. I first defined a simple logistic regression model. This model allowed me to establish a baseline AUC score and classification report. The LR model had a low AUC score of 0.695, which showed that there is a clear need for a more complex model, which is why after that I then defined a random forest classifier, or RFC model. Based on some of the academic papers I read for this project, RFC models typically achieve a higher AUC score for predicting diabetes risk. The RFC AUC score was also quite low and too slow. Due to this, I moved on to an MLP classifier. The MLP model, in theory, had the highest potential for maximizing the AUC score due to its powerful ability to learn complex, nonlinear boundaries. The initial model still had a low AUC score of 0.6781. However, since I was personally interested in working more with a neural network model, I decided to proceed with the MLP classifier. My next step was to then tune this MLP model in hopes that I could achieve a better AUC score. I performed a manual iterative tuning process. 3 different combinations were tested. Each had a different hidden layer size and learning rate. I found that the best model had a 50 by 20 hidden layers and a learning rate of 0.01. Despite the manual tuning process, the optimization failed. The final and best-tuned MLP classifier only achieved an AUC of 0.69528. This score is basically equivalent to the logistic regression baseline, which showed a complete lack of progress. The ROC curve for the final tuned MLP overlaps entirely with the LR baseline. This visually confirms that the optimization process failed, and it makes it clear that the model lacked any true separation power and failed to move the curve away from the random guess line. So let's talk about the challenges that I faced while working on this project. The core challenge of this project was the tuning method. Manual tuning is basically trial and error. This is a very inefficient way to optimize the model and contributed to the model's poor performance. Secondly, I believe that the atom solver for the MLP became frozen halfway to the optimal solution. It is possible that the solver got stuck at a local minimum due to the complexity of the cost function, leading to poor results. Future work must address the root cause of the failure. We must drastically reduce the input complexity through focused feature engineering. In the future, the focus should be not on the entire features, but rather on a reduced number of features through the creation of specific and relevant interaction terms and ratios, such as the age and BMI ratio, the LDL/HDL ratios, and so on. We should also explore a different model, such as linear support vector, or SVM. Some academic papers suggest that an SVM model is very effective for diabetes risk prediction. And finally, I would like to learn a little bit more about other optimization methods for MLPs that could potentially boost the performance and how to implement them. So, in conclusion, in this project I compared 3 models, LR, RFC, and MLP, to determine what the best model is for diabetes risk prediction. I manually tuned the MLP model in an attempt to achieve better performance, but I was unsuccessful. While the final AUC was only 0.6953, the project successfully highlighted the crucial and real-world practical challenges of optimization. This project allowed me to explore various models and learn more about neural networks, which is something that I was hoping to get out of this project. With that, I would like to thank you for listening to my presentation and thank you for a great quarter. Here are my sources. They are also included in my code.